So I prepared a presentation about formal verification, and it's actually on GitHub as well. So if you go to github.com/Teiml/presentations, then it's there as well. So it's an HTML presentation. So I thought hard about how to structure this talk, and I kind of made a dependency graph for all the things that you might want to know in order to learn about formal verification. And it quickly occurred to me that it would be impossible to fit everything into one talk. So I decided to today talk about the bottom left three, EVM, K, and KVM, and save the other four for next time. So today we're going to talk about these three. As such, the goals of the talk will be to kind of show you how the EVM works under the hood, show you how K works in a way, and then we'll put the two things together and we'll construct KEVM.
What is K?
Yeah, that's what is the contents of the talk.
Okay.
So, yeah. Indeed. Okay. So let's start with.
So you want to be continue the recording?
Yes.
Yes, we have indeed.
It's a recording online.
Yeah, and also when I was preparing this presentation, I wanted to make it accessible and technical. So I want to make it so that everyone can understand it, but at the same time we go into the nitty-gritty inner core of the topics. So let's begin. So the EVM stands for the Ethereum Virtual Machine, and a virtual machine is essentially an execution environment, in this case for Ethereum transactions. The first thing to note is that there are multiple versions of the EVM. A good rule of thumb is that all of EVM's inner workings can be constructed from the definitions of the opcodes of the virtual machine, because these immediately give rise to data structures such as word and address, and what in academia are called stores, such as stack, memory, storage, call stack, gas, program counter, and so on. So let's begin with the very first version of the EVM, which was Frontier. So in Frontier, which was the very first version, so it was released together with the Genesis block about 3 years ago. Programs, as always, are abstracted as numbers, and the level of implementation is a bytecode. Each byte can be represented by 2 hexadecimal numbers, as always, 0 through F. So now let's look at some of the most popular opcodes. So I actually did some Python magic, and I was able to find the most popular opcodes for, well, basically any contract in the world. So for the GNO token, the most popular opcodes are push1, which just takes the next byte in the bytecode and pushes it onto the stack. Fun fact, it's also the only opcode that interacts directly with the bytecode. So it's the only opcode that has the power to ignore other bytes and interpret them as data instead of as opcodes. Did that make sense? Like you have a bunch of opcodes, but then if you have a push opcode, then the following bytes will not be interpreted as opcodes; they'll be interpreted as data for the push.
Maybe we need kind of one step. What are opcodes actually?
Oh, so opcodes are instructions of a virtual machine.
Yeah.
No, I'm gonna show like the opcodes. I'm gonna discuss it all. I just wanted to point out a few before I do that. Or do you want to say something?
I feel like certain machines what opcode is.
Just think about solidity. Solidity is a high-level program language. You need a compiler that translates this to low-level language. This is Ethereum virtual machine.
Yeah, so
It's like in a computer, it's a machine language.
yeah, on a very low level, a computer can do the calculation is broken down to very small instructions. So very small instructions, just for example, adding two numbers, or kind of going. You have a bunch of data and just kind of take a pointer for this data and just saying something like set the pointer one step forward, or you have a stack of data. So yeah, really like kind of is one data point and then the next one is on top of it and so on. You just add another data point or kind of bit or byte to the stack. And on that level, kind of the smallest possible instructions.
If you think, for example, doing a sum of numbers, it's not just one operation. You need to get it from memory, put it, and then the other parameter, and then take it back to where you want to use it. So actually, it's a lot of operations.
Right.
Yeah, exactly. Cool. So yeah,
just to make one more. What this is each byte. So the opcodes or the data should be, of course, be represented as small as possible. So how many opcodes does Ethereum actually have? And Dominik might help you with. Do you know?
Like right now, I think it's like 138 or something like that.
Yeah. So the opcodes you have kind of in general you have virtual machines, Java VM, Java virtual machine, and so on. They are kind of just virtual machines that have a set of opcodes where you can do kind of normal computer programs. And the EVM, Ethereum virtual machine, was a virtual machine that supports kind of general stuff, so general computation, but it has a bunch of opcodes that are very specific to Ethereum. So that is, for example, validating a signature.
Yeah, I'll go through all that.
So but yeah, it's going already pointed out so that you have kind of just because of the addressing scheme, you can have 256 at max different opcodes, and currently like 200 something, whatever number it is, are already in use. So basically, it means the Ethereum system can, if needed, introduce this very limited number of new opcodes, additional opcodes to enable additional stuff.
Yeah. It's also why it's very dangerous to use currently not use opcode as a placeholder for reverting. And the reason is in the future, the opcode could gain semantics, in which case the execution would be different than the current version of EVM. Cool. So
on that level is everything. So far, everyone is kind of here.
Yeah, so basically just to summarize in one sentence maybe, the EVM is the execution environment for all Ethereum transactions, and in order to execute stuff, you need to be able to set instructions, and the instructions are the opcodes. Right, so an instruction could be push. So for example, this could be a basic EVM program. And then add whatever the number for add is, I don't remember. So unless I'm mistaken, 60 is push 1. So it pushes 0, 0. So we have the stack is composed of 0, 0, in other words, 0. Then we have 60, which is push 1 again. And we have 0, 1 here. So now we have 0, 1 on the stack. And then we do add. And what add does, it pops the top two elements of the stack, and it replaces it with the sum, modulo to the 256. So then we get the result to be 1. Right? And then you could maybe do, you could maybe copy it into memory with some other opcode. So you could do mstore 8, which just stores a single byte, and then you could do return, and you could pass in the address of the memory where you stored this. And that would be a very simple program that all it would do is every time you would call it, it would add 0 and 1 and give you the answer. Is that clear? Cool. So some of the most popular opcodes are push 1, pop, which just deletes the top element, swap 1, which takes the first and 2 elements of the stack and it swaps them, do 2, which duplicates the second element and places it on top of the stack, so now it becomes the third element, and add, which we already saw the semantics of right here. It adds 2 numbers modulo to 6.
And you said these are like the most popular opcodes.
So that's a really good question. Yes, for the Geno token. And now the follow-up question could be, are they the most popular opcodes overall? So I also ran this on another contract, and that is the latest version of the Gnosis state. And I got a extremely similar result. So yes, they're probably very popular. Now let's have a look at the other opcodes. So this was just kind of like a teaser. So I categorized the opcodes into 2 categories: generic, that could be present in any virtual machine, and blockchain specific, that are specific to the blockchain environment. The first subcategory would be opcodes that deal with the control flow. So stop is very simple, it just halts execution successfully. Jump is very simple as well, it jumps to a different program counter. Jump I is very simple as well, it's a conditional jump. So it pops the top element of the stack, and if it's 1, then it jumps, and if it's 0, it doesn't. You can only jump to something called the jump destination. So we also have a jump dest opcode. And you can also read the current program counter from the program and push it onto the stack. So that's the semantics of the first 5 opcodes on the list.
Is this program counter counting?
It's counting the program counter. So every time you execute an opcode, you increase the program counter.
Oh,
Okay. So if we were to go through the execution of this program right here, the program counter would probably start at 0 or 1, whichever the indexing is appropriate. So it would start at 0. Then once it executed this opcode, it would go up to 2. Once it executed this one, it would go up to 2. Then add would go up to 3. Then mstore, I think, takes like 2 variables, so maybe it would go up to 6. And then return, and it would go up to 9, right? So, sorry, actually, that was not correct. Because mstore and return, they take arguments from the stack rather than from the bytecode. So each of these would increment it only by 1. In fact, every single opcode increments it by 1, except for the push opcode, right? Because that's the one that interprets the following bytes as data, not as outputs.
But what actually does this tell us that these are the most popular opcodes? Is that related to specific functions of how GNOs are used?
Not really, no, because the Gnosis state and the GNO token are extremely different contracts, and yet they still have the most popular opcodes, pretty much the same.
But
mainly dependent on how so kind of the contracts are written in Solidity, or that's what. So this is higher level language, and in this language you have constructs like adding to variables. But under the hood, kind of that is compiled down to those very much smaller instructions. And yeah, probably you have different options how you kind of do those higher level instructions, how you break them down to those very smaller level instructions, and probably you could create another smart contract language that would use kind of use different opcodes more. Although I assume there are just some opcodes that you will always need more often, because they're just very, very fundamental to doing anything.
Any kind of like stack operations, handling what kind of memory is used within the contract execution, that's just generically so important.
Yeah, if you
But
guys want to,
then Alexei, he did a very detailed audit of our contracts on this opcode level even, and he analyzed the solidity, compiles down to opcodes, but really inefficiently, so they're using lots of opcodes, which are not really necessary to get to the same result as you actually want to, based on your solidity code. So
look,
many of those are probably not really necessary, it's just that solidity is inefficiently compiling it to opcodes.
so analyzing this would help us to make our code more efficient or help others to use it more efficiently?
yes.
More.
Yeah, I mean, in theory, yes. In practice, that is not usually what it's used for. I would say it's used for, one of three things. The first one is to make the code more efficient. The second one could be to do stuff that Solidity doesn't support, because Solidity doesn't have support for all the functionality of the virtual machine. And the third one could be to do formal verification.
Nice.
I would say the main trade-off is you have this low-level virtual machine. If you write directly in that, it would be more efficient, but it's not readable and it doesn't scale. I mean, you want to do all the functionality, maybe it will take you forever. Right?
Yeah.
If you do it with Solidity, we'll have a lot of redundancy of code that doesn't do something useful, and maybe some things are maybe insecure too, because the compiler can have a bug and put code that you don't expect, but you can read the code easily. Okay. So that's one of the main trade-offs.
Yeah, I totally agree. So, for example, this program that we wrote, that all it does is it takes 0 and 1 and adds it and returns it. In Solidity, that would be one line. Right? But in the opcode level, it's like 12 opcodes.
Now, if you wrote return 10 in Solidity and compiled that to bytecode, would it look like what you
No,
did
it
for
wouldn't.
us today?
And the reason is the Solidity compiler is very inefficient. So the Solidity compiler is worse than us collectively writing the opcode. It's worse than us.
Usually compilers need to make assumptions of
Yeah, but it doesn't make mistakes. So I guess that's yeah. Since you guys were so interested in the most popular opcodes, this is the entire frequency density for the Gnosis stage. So exactly as Stefan was saying, stack operations are by far the most popular, and then also memory is dealt with quite a lot, mstore and mload, and that's pretty much it. There's very little of other opcodes. So now let's just briefly go through all of the other ones. Oops, right here. There we go. So there's a bunch of arithmetic and bit functions and predicates, such as adding two numbers modulo to the 256, A0, which takes the top element of the stack, and if it's 0, it returns true, and if it's not, it returns false, it returns 0. Everything is represented as zeros and ones, and equality greater than and or, which does exactly what you would expect them to in the real world, and many other ones. There's a bunch of stack operations that we've already touched upon, such as push 1 through 32, which is actually 32 different opcodes and allows you to push data onto the stack from the bytecode itself. Pop, which does the opposite. Dupe and swap, which we've also already discussed, both also in 16 different versions. Next, we have opcodes that deal with memory. So you can read and write to memory, and you can read and write to storage. And noteworthy is the self-destruct opcode, which it takes one element from the stack, and it forwards all of the ether of the current contract to that address, and then it removes the current contract from, well, it depends which version of the EVM. Before, it would just null it, but now it actually removes it from the state tree as well. But since we're talking about frontier here, it just nulls it. So what does it mean to null an account? It means to reset its balance, its storage, its nonce, and its code. So every account in Ethereum has those 4 fields as well as an address. Obviously. So the blockchain-specific opcodes, they actually occur quite rarely. The only one that is common is SHA-3, which is a very confusing name because it's actually the KEKAK 256 hash function. It's not the SHA-3 function, so don't get confused. But that's another. No, so the reason was this that this was finalized. Sorry, the Ethereum was the Ethereum frontier release was finalized before SHA-3 was finalized, the standard for the hash function. And when that changed, Ethereum obviously couldn't change anymore. So then we have basically a bunch of opcodes to get information about the current transaction, about either the current block or the last 256 blocks, and to read and write to other smart contracts in the network. And finally, we have opcodes that give rise to a bunch of stores that we haven't discussed yet, such as the call value of a transaction, the call data, and the return field, and the logs and gas field. Okay, so now we have an overview of every single opcode that was released in 2015. I write that there are 65 opcodes because I kind of collapsed these 65 opcodes into 4. Yeah, so this gets reduced by something like whatever. Yeah.
How do you swap an odd number of?
How do you swap?
Is a swap just like a cyclic thing, or you can't swap an odd number? You can't swap more than 2 things, really. So what is swap 3, for example?
Swap 3 swaps the first and the third element. Or actually, no. I said that wrong. Swap 3 swaps the first and the fourth element.
Okay. Maybe the best way to explain this would be to open Remix and run a very small program to see.
Yes, yeah, that's not a bad idea as well. So if you guys want to learn more about the EVM, one of the ways to do that, well, I would just run KEVM because I think that's the best way. But you could also, although I do not know how to enter bytecode programs into Remix.
Oh no, you can write.
Oh, you can write. Yeah, you can also do
you can
that.
see how the transaction can be.
So let's do
applied.
that. So we have a contract.
What if we write your adding
And
return 0, 1?
Let's
It's
write
in the
the.
context of
Oops. So let's make it a function that returns an unsigned integer, and its semantics, will be that all it will do is it will return 1 plus 0. So now let's deploy this contract, and let's run the test function. So you get a transaction back, and you can click on this beautiful field called debug. No, it's actually pretty cool. And then you can step through the entire execution of that function and see exactly what is happening.
Translation of the utility code into the opcodes, and then you can see how the stack and memory is changing during the execution of this function.
Right. So Uh, yeah, so basically, you can also, Stefan, do you know where where I can see the opcode of the contract?
It's up there, it was there. Top left on the right side, it's.
Oh, right. Okay, and then there's another, there's like a pop-up, where it shows me everything. Do you know how to get there? Oh, is it maybe? Yes, exactly what I wanted. So this is another way to see it. I think the best way, because you have like all the opcodes here. So this is exactly the opcodes it generated. So let's see where the code that we wrote is like going to be there. But I mean, it doesn't matter. As you can see, it's really like complicated, right? It's so much more than it would require. Literally, all it would require is this. But that's assuming that it's a fallback function, it's not a fallback function. So it would require a little bit more, but still not much more than this. Okay? And what you can also do is you can use the debugger to step through the entire execution. And therefore, you see both what is on the stack and what is in memory, as well as all of the other stores of the Ethereum virtual machine, such as the call stack, the call data, and the return data. So this is actually really cool. Yeah, thanks for bringing this up. This is the best way, I think, to learn about the EVM. Cool. So let's just go back to the presentation. And yeah, that's pretty much it. That's all I wanted to say about the opcodes. So
maybe kind of one more word on opcode. So there is when Ethereum makes once in a while a hard fork, and the next hard fork was scheduled for November. That there were some issues, so right now it's scheduled for February. And there is always a discussion to introduce new opcodes. So the advantage of having an opcode is that you can do things much cheaper. So in theory, those opcodes that exist allow you to do everything that you can imagine. So that would be called Turing complete. So with a bunch of opcodes, and you would need much less than this 100. I guess you need like something like 10 opcodes. It was not 10 opcodes. You are able theoretically to describe every program that you can imagine. However, if you have more opcodes, it allows you to do the same thing more efficiently. So one example is this hash code, this hash function. You can kind of do like 20,000 steps to perform this hash function, or you introduce one opcode that just does it. So instead of doing 20,000 steps, you do just one step. This opcode is just defined as do this whatever the hash function does. So it takes some data and do some calculations, and you get a hash of it. So the trade-off is you could kind of have the long list of opcodes, but even kind of for the addressing, so to give every opcode a name, if you have more than 256 opcodes, you would need more storage to even kind of name them. There are a bunch of other compromises. So if you have very easy opcodes, you can do computer hardware that exactly can kind of where the hardware is running this opcode on hardware level. You wire the hardware in a way that can do this small instructions very efficiently. If your set of opcodes is bigger, then you would kind of need to create specialized hardware. So there's a trade-off between specializing and being generic. And so there's always discussion around adding new opcodes or not. So one example of opcodes that was added a year after Frontier was an opcode that would allow the zero knowledge proof stuff. So the stuff we are working on with the diffusion exchange. But then again, this opcode is only good for some forms of this zero knowledge technology. Now it's moving forward, and you would kind of need a new opcode. So that's the high level trade-off. And for the next hard forks, there are like at least one new opcode, and I think there's
5 new opcodes.
Yeah.
5 new opcodes in the next.
Yes.
You call to.
There's call to. I'm gonna go through. I'm gonna go through everything.
Okay.
I'm gonna go through. Yeah. There's 5. Cool.
So
So
we can one last high level comment. So the approach of Ethereum is to have this one virtual machine. There is in blockchain world there is another approach that is the approach Polkadot, for example, is choosing. They say, let's have different execution environments. The EVM would be one execution environment, but let's allow kind of different virtual machines with different sets of opcodes that are specialized for different things, and try to connect them all. So to have the Polkadot network as a center, where it's just about collecting transactions, collecting data, and then have all those different execution environments which are specialized. So instead of having a fight kind of on should we introduce software, shouldn't we? You just would add a new execution environment with its own set. So those are kind of the very high level trends or discussions or tendencies where blockchain world could evolve.
Isn't that what Cosmos is doing as well?
Yeah, because Polkadot and Cosmos are fairly similar. They have differences, but on that, that's kind of the general scheme that they say, well, let's have different blockchains or execution environments that are somewhat connected through a hub that are specialized for different stuff. While Ethereum is trying to be the everything for everything.
I have one question
Sure.
regarding these more sophisticated opcodes like the hash op3. Now, we're sort of including this as an opcode so that we don't have to compile it down to like 20,000 operations or something. But those 20,000 operations that are required to hash something still need to be performed somewhere.
Right.
So is this just something that tells the machine, all right, this
Right.
corresponds to these 20,000 operations? It's still being performed.
Right.
No. So it actually allows. No, I don't think that's how it works. Like the clients, they implement it natively.
Yes.
Well, I mean,
So
They
where
have
is
to
the calculation being performed?
Yes.
Well.
Okay.
You have to separate a few things. So the client itself could run in a virtual machine. So you can have a virtual machine on your computer running Linux, and within this Linux, there you run this. So whether it runs or how it runs, there can be many layers of abstraction. But of course, the ultimate or goal would be that you can run this opcodes directly from the machine. But then the machine would actually have to have that functionality. So, but why do we need this opcodes at all, or why is it important to kind of bring it down to instead of having 10,000 opcodes having fun? You point out correctly in the end, this still needs to be done. Is every of those opcodes has a specific cost associated to it?
Oh, yeah.
So that's the gas.
Okay,
Yeah.
So every of those opcodes kind of adding costs 5 gas. Accessing storage costs 20, and making up those numbers. But writing to storage is kind of one of the most costly things. It costs like 20,000 instead of 5. I'm making those numbers up, but it's much more expensive writing to storage than everything else. So in a way, when you introduce a new opcode like the SHA, you're subsidizing specific things. So so those costs are necessary to make the system kind of immune against spam attacks. So if someone writes a malicious code that's really hard to perform and kind of would slow down the network, therefore it's important to have those costs. However, for something like a hash function, we know, well, I mean, you could express it with this 20,000 steps, but at the end of the day, we know, okay, hash function, that's something the computer can calculate. So we kind of manually say, well, we just set the cost to something very small, because we can be sure that it is something that's actually not that hard. But kind of to, in general, kind of give everything a price is hard, because someone who's malicious might come up with some combination of using those very small codes to do something that's in reality much harder.
So next, I was gonna have a slide, but it's not on the presentation. That's what you get when you write the presentation in code, is that it becomes buggy. So this slide was meant to be this. So there are also other ways to categorize the opcodes than the ones I chose. Examples include whether they change the state. So the only ones that change the state of the blockchain are actually the ones that change the permanent storage. Memory and stack are transient storage locations. So log, store, call, create, and self-destruct. You can also categorize it by how much stack they eat up, everything from nullary stack operations, which would include just stuff that reads stuff very, very easily. So, for example, stop, jump, program counter. Let's see, what else would be a null stack operation, doesn't take any stack at all. Address, balance, origin, color, and gas price. These 5 as well as anything that ends with size, except this one, size. Because that also you need to specify which address you want to use. But for example, this one would be a nullary stack operation, doesn't take up any stack. You call it and it gives you an answer. And then the worst case are operations that take up 6 elements of the stack. So an example is call and I believe it's call code that take up 6 elements from the stack, because they require you to set the address, set how much value you're transferring to that address, then set the memory location of the code that you want to send as part of the call, and that takes up 2 stack locations. And then finally, if you get a return value, where in the memory should you put it back, which takes up 2 more stack memory stack operations. So in total, there's 6 arguments that go into this function from the stack. And as Martin already perfectly mentioned, the opcodes are also categorized by how much gas they need, which is either a constant or a function. And that gives rise to a number of equivalence classes on the opcodes, which are in the Geth implementation called G0 for opcodes that don't cost any gas at all, G very low, and so on. Now you might ask, what's the point of gas? Why do I need to pay it? So there's 2 main reasons. The first one is to prevent infinite loops. Right? If there's a fixed amount of gas, a fixed amount of ether, therefore a fixed amount of gas, then you will never be able to do an infinite loop. And the second is to incentivize people to optimize their code for good execution, fast execution of the Ethereum network.
And then energy costs for it.
Yes, exactly, which is a related stuff. Cool. So let's go back to the presentation. When I said that there's all the inner workings of the EVM can be constructed from the opcodes, I actually lied, because the EVM has these things called precompiled contracts, which are just contracts at the address 1, 2, 3, and 4 that do a specific thing. And the EVM has been criticized for not having these as simply opcodes. And actually, I don't know what the reason why they chose this implementation, but it definitely makes, for example, formal reasoning very, very difficult. And it just makes it more of a pain in the butt, because the reason is that, like, as we'll see in the next presentation, formal verification uses symbolic reasoning. And whenever you generate an address at random in KEVM, you always have to assume that it's not one of these 4 addresses. So it just makes everything more complicated. But if some of you know the reasoning for this implementation, I would love to hear it. So yeah, I mean, it could have been various things. It could have been something like the fact that the opcodes were finalized, but then afterwards they wanted to also add support for these 4 functions. I think that's the best reason that I can figure out. Cool. So now let's talk about the other versions of the EVM very, very quickly. This was the hard part. 99% of everything is same across all the versions. So we got through the hard part. Now let's update it with recent improvements. Some notation to get started. An Ethereum improvement proposal, which comes from the days of when the internet was being born, is a proposed change to the protocol of Ethereum. And when they get included in the main chain, it's called hard fork. Note that all of the upgrades of the Ethereum virtual machine require a hard fork, but not all of the hard forks deal with the Ethereum virtual machine. There are many examples where hard forks had nothing to do with the Ethereum virtual machine. They can also change balances arbitrarily, like the DAO fork. The Ethereum protocol also includes specification for the clients. So when the client specification changes, that requires a hard fork, as well as decrease the block reward and change difficulty, which have been changed multiple times. The first hard fork to impact the EVM was in March, and it was very simple. It was basically a bug fix to 2 bugs in the EVM. The first one was that, break it down. So if you were to create a contract through a transaction, it would cost 21,000 gas. But if you were to make a transaction to a contract that we'll call the create opcode, that we saw earlier, so we were meant to make a transaction to the create opcode, then it would cost 21,000 for this, and the create opcode cost 32,000. So basically, it made this too cheap, because you would save 32,000 for the create opcode. So what Homestead did is it made the cost of a transaction that creates a contract naturally 53,000, which is what it is today. And introduced a new opcode called delegate call, which was basically a bug fix to call code, because that did not preserve message.sender and message.value when it was called, which is probably what you would want from an opcode with that semantics. And then there were
like this kind of call opcode is kind of useless, but because it has been used in the past, we cannot just assign like a different functionality to it right now. So it's kind of a useless opcode that we know will always be there, but it won't be used anymore.
Exactly. Then there were 2 more hard forks, and they were kind of minor. They were mainly concerned with preventing the denial of service attacks that Ethereum was facing at the time of DEFCON 2. So it increased the cost of gas for some read and write opcodes, such as self-destruct and external code size that requires so much computation on the part of the client, yet they cost so little gas before. So basically, again, it was kind of like a bug fix. Cool.
I just wanted to ask whether we're going to finish at 1 or not, because
I think I have about 20 more minutes.
okay. So the food is here already. I'm sure we can eat it in 15 minutes. So,
Yeah, 15 minutes.
Yeah,
That's
I'll
okay.
just set it up in the big kitchen then. Once we're done. Yeah.
Cool.
Thank you.
Awesome. You just take a drink and then I'll push through it. So Byzantium introduced 4 new opcodes, and yeah, and 4 new precompiled contracts, which enabled the use of
Maybe
CK stars.
skip that and go directly to the K part. I mean, you have
Yeah, that's why I'm skipping. That's why I'm skipping the semantics of all of these. And finally, for completion, the new proposed change to the EVM is called Constantinople, and 5 new opcodes will be added to the Ethereum virtual machine.
That's shift
Shift left, shift right, and arithmetic shift right. I'm not sure about their semantics. Sorry. There's some bit functions, yeah. Cool. So that was actually what I consider the hardest part of the talk, and now it's going to be part. So let's talk about K. What is K? K is a programming language to define the syntax and semantics of programming languages. Now, I don't say other programming languages because it can also define the syntax and semantics of itself. So there's 2 words there. The first one is syntax, and the second one is semantics. Syntax is how a language looks, and semantics is what a language means. And in the previous version of the presentation, I had like formal definitions of these, but then I realized I probably wouldn't have enough time, so I'm glad I dropped that out. So in K, you have 3 different declarations: syntax for syntactic rules, which are done using Bacher-Nor notation, Bacher-Nor form. That's what BNF stands for. For example, in this way, this says that this defines the syntax of 2 arithmetic operations called plus and times, and says that if you have 2 arithmetic expressions and you plus them together, you will also get an arithmetic expression. And we also say that times binds tighter than plus, and that it's the other type of declaration we can have is configuration, which actually defines the stores of the language using an XML notation. And finally, we can have semantic rules that rewrite terms in the various stores and actually form the whole point of what K is about. So in order for this presentation, I actually wrote a language in K to illustrate how K works, because I didn't find any that would be simple enough, so I wrote my own. And it's a language that functions as a calculator. So here it is. So this is the language that functions as a calculator on integers, and it can do anything. It supports bracketing, so it's i.e. changing the order of computation, and it supports just about everything that you might expect from a calculator, including negative and subtraction. I separated those 2 so as not to have multiple execution paths.
So can you explain one of those lines?
Yes, of course. So we start here by saying that an arithmetic expression could be either an integer, or it could be negative an integer, or it could be another arithmetic expression, for example, 5 or -3, divided by another arithmetic expression, for example, 10 or -4. And similarly, we also define the syntax of divided, times, plus, minus, and grouping. And we give it order of preference using this. And then this, don't worry about it for now. Actually, don't worry about it at all. And
preference?
So basically, we want times and divided to bind tighter than plus and minus. And furthermore, we also have to define the semantics of these. What are these symbols, plus and minus? What do they actually mean in our language? So we do that by saying whenever we have a variable I1 minus a variable I2, it will always rewrite as I1 minus int I2. And now your question is, what is minus int? So it's a k built-in operator on arithmetic integers.
Would you say it's like the opcode of K?
I would say exactly that.
I have a question about this.
Yes.
How do you declare order of operations, or how is order of operations declared in this?
This symbol right here.
Oh, okay.
How much opcodes does K have?
I don't know. I mean, they're not really opcodes. They're like built-in stuff, and you can basically import more libraries to add more functionality. So it's like a regular programming language, which allows for importing and exporting.
But then basically you have to define you have to map the opcodes of the language that you're verifying onto those native opcodes and opcodes. So that seems like something that's probably dangerous.
Yes, you're absolutely right. There could be a bug in the way EVM is defined in K. So that's a valid like reservation. In fact, it's something that we'll never get over with software. There's always a possibility of a bug there. Yeah. I think the difference of executing it in the EVM versus executing it in K is that in the EVM you can only do execution that is concrete, while K EVM gives rise to symbolic execution, which is what you want to do if you want to formally verify specification, which is what I'll talk about next time. Okay, I have 7 more minutes left.
Shortly, kind of still give you an idea of what that means is concrete execution is, of course, you have values for each variable, you have a value, and symbolic execution means more like assuming kind of this variable can have any value. What is anything that, or what are things that are in general possible? So you're trying to make very, very general statements about the program. You're trying to make statements about this program, no matter what the input is, no matter what the state is, no matter no matter what happens, it will never reach a specific state. So step that we want to do is for the verification state, no matter what happens with the state, it will never reach a state where money is frozen forever. That's kind of a statement you're trying to come up with formal verification. And again, because the past is there is this K language description, and this language description is much easier to kind of create those proofs about those general statements. So the first step is to kind of map the EVM to K, and then if we have an automatic translation, then we can kind of try to come up with those proofs.
You're absolutely right. So in other words, KEVM is an interpreter for the Ethereum virtual machine in K. So I have 6 minutes left, so let's rush through this. Let's start with specifying the configuration of KEVM. So I kind of made it easy by separating out our opcodes into categories. So this gives rise, we'll definitely want some program counter. We'll definitely want, by the way, this version that I have right here, it also includes the new opcodes, such as delegate call. We'll also want stuff like, we also want the status code to know whether it's returned something successful or something unsuccessful. We'll want a memory. We'll want some storage. And we'll want some block info. And given the fact that we have calls, we'll also want a call stack that will allow us to call other contracts and have the execution environment there be different than from the current one. And that's basically what it becomes. So this is kind of a naive implementation of the EVM in K. It has, I'll go through this in 1 second. It has a status code, as we said. it has a call state, which has everything that you might need for the execution of an Ethereum transaction, or I should say message call. You have a bunch of accounts that each have, exactly as we said before, an address, balance, code, storage, and a nonce. And finally, you have information about the blog and some random stuff that also has to be there. The way we write the configuration is we always write what will it be initialized with. So most of the stuff gets initialized with 0 if it's an integer, and in K, if you write dot, it means nothing. So if you write dot map, it's an empty map. So this is, by the way, the configuration that we have here, it is a subset of the real K configuration. So if you were to write this in our K code, it would actually match the actual configuration. So it's not that far from the truth. It's a naive implementation, but it's still pretty good. This is the actual one. So the reason the actual one is much more complicated is the KEVM is not only an execution environment. You can also use it as an actual EVM node, which is what Cardano is doing with ELA. They are using KEVM as an actual node for the Cardano blockchain, and for that you need a lot of other things than in our implementation. Cool. So let's skip syntax to talk directly about semantics of KEVM. And I have a few minutes, so let's just go through it. Most of the time, we don't want to be altering the configuration directly from the opcodes. Instead, we'll define helper functions that will begin with hash. This increases safetiness and modularity of our code. So let's start at the end. Let's start with okay. So when we'll define this internal operation called -halt, and when we get it, we want it to consume all further opcodes and halt execution. And the way we do that is using this. Here there are 3 things that you haven't seen yet. Let's start with what you have seen. Rule is a semantic rule. K is a cell that this semantic rule will use. This is an internal opcode that we defined, and then this is what you haven't seen. So this is the K way of saying and then. So it's the quick K way of saying of giving time or order to operations, and then you also haven't seen this, which is everything else. So if we have something like this, this will match every time there is a halt on the top of the K cell, because it has to be on the top, and it doesn't matter what there is afterwards. And if that halt is followed by, this is the K way of saying anything of type opcode, then it will get rewritten to nothing. So, in other words, it will consume all of the opcodes that are to the left of it, which is exactly what you would want, right? If you halt the machine, well, you wouldn't want it to keep on computing stuff. Next, we'll need something to be able to set the status code. So we'll define this internal opcode called NSC, which all it does is it halts and it copies whatever we pass it into the status code. So now here's a question for you. Assuming a status code of let's call it EVMC underscore success, what should set it? And I'll give you a hint. There's 2 options. Either the program finishes execution, i.e. it runs through all of the bytecode, or it halts somewhere in the middle. And that's the answer as well. So either program is fully executed, i.e. we want to return success when we've reached the end of the bytecode, or we want to halt at a specific opcode. Which opcodes should result in a successful halt, do you think? So an example could be the stop opcode. All it does is halts execution, everything was fine. Another example could be the return opcode. Another example could be the self-destruct opcode. And what was the 4th one? In fact, I forgot, so let's have a look. Oh, actually, those were the only 3. So These are the only times in the Ethereum virtual machine where you would want to quit an execution successfully. Cool. And now I'll just give two examples very quick. I think they'll both take 1 minute. And the first one is how are we actually going to execute opcodes? So we're going to start with just one item in the case cell, hash execute. And to give it some semantics, we're going to give it, by the way, I didn't think of this, but I think it's pretty cool. We're going to give it two semantic rules. The first one, it says that whenever this occurs, to the left of it, nothing will get rewritten to next. So what is the imperative meaning of this? This means that execute will keep putting next in front of it. We'll put it there, and once next gets executed, we'll put another one. Once that gets executed, we'll put another one. It will forever, that's its only job, is it will put next to it if there's nothing next to it. And in order for it to halt at some point, we also say that, well, if there is a halt and then there's an execute, well, then finally the execute disappears. Does that make sense? I think it's quite understandable, but I realized that it's been quite an intensive day. So now I just want to give one example, but maybe I'll do it next time. Or do you guys want to see it? Okay, cool. So
2 minutes or 20 minutes?
Yeah, I mean, I can do it next time. It's not a problem.
I think Ben and I want.
That's good. Good.
With the Tau.
So here's the. I mean, it's not very long. It's literally like, I can show you. It's like 4 slides.
Let's do it. Come on.
Okay, so basically, we just defined the semantics of execute, but we also want to define the semantics of next. So that's going to be a little bit more complicated. What should next do? What should the actual execution of an Ethereum opcode be? And if we were to think about it really hard, like the K people did, this guy called Everett, and he'll be at DEF CON as well, he thought of all of this, so you can give him props. So what it should do is, it should first check whether the opcode can be executed. Next, it should execute it, and next, it should increment the program counter. Right? It's very basic expectation of we would want execution of output Ethereum opcodes to be like. Whether it can be executed, it should say whether it's a valid opcode, whether our stack is large enough for the opcode, and don't worry about this. And then finally, it should pull the arguments from the word stack and actually put them next to the opcode. I think they should have had a different name than this one because it has the same name, but they're different functions. But I think there's rooms for many improvements in KEVM. And finally, we should deduct gas and then actually execute the opcode. So the EVM gas is deducted before the opcode is executed. So that was the semantics of next. Now let's apply that, everything we learned today, to to try to figure out the semantics of an actual cool opcode on the Ethereum virtual machine. So which one should we pick? So actually, we're going to pick the hardest one, and that's call. So let's have a look. So how are we going to structure the semantics of the call opcode? So this is the actual code. I just wanted to give you a taste of what it looks like, but we'll break it down. So this is actually not that important. It's just how it actually looks like in code. As you can see, it's quite readable. It's much more readable than reading the Go implementation, the Go code. If you actually want to learn about DVM, you can either read the client code or you can read this, and this is much more readable. But let's break it down even further. So if we have a call, and by the way, this already assumes that we have the arguments in front of it. So we've already executed next, and we put everything there. Then we want to do just 3 things. We want to check whether the call can be executed. We want to call it, and then we want to return whatever answer we get. This checks the call depth and the balance is large enough. This checks whether the contract is not a precompiled one that we're calling. And one more thing that I forgot. And and then we push the call state and we transfer whatever funds that we want to transfer and we make the call. Now, what does it mean to make the call? It means to initiate the virtual machine, so to null it, to call execute. Now, we're going to use what we just learned, and we already know that execute will keep on putting next in front of it until it will receive a halt. So I'm already assuming that the execution basically takes steps in this little space right here. So once we've executed all of the opcodes and we finally reach the halt, then what should a halt and a return do? Now, just one last complicated thing I'm going to say in the entire talk. So the only problem we have right now is we specified halt over here, but we said that halt should always okay, what did I want to say? So halt and yes. So yes, okay. So we said that halt should oh, it's because I didn't include the code here. Okay, that's why I can't find it. So I thought it was there. The one where the actual semantics of halt. Do we have that? Oh, here it is. Okay, so we said that what halt does is it will consume any single opcode that is in the back of it. But if we have halt and return, we don't want it to consume stuff. We want it to actually do something. And that's where like case sorts come in. So we're going to declare return as a different sort than this. So this rule will only apply if this is an opcode, which also includes KVM internal operations. But it will not apply when we have something like this. And that's why this we can give it different semantics. And in particular, what we'll give it is we'll drop the execution environment that we're in. We'll push one. This was added in one of the hard forks, and basically that signifies that the transaction was successful because revert now is not doesn't consume all the gas, so it's not enough to say whether the transaction ran out of gas to know whether it was successful or not. And finally, we give a refund for whatever gas was not spent. And this is the most important thing of it all, of the end, is that whatever was returned from the call, we put it to local memory. And that is the entire semantics of a call operation, from it being in the case cell to actually putting the return value back into memory of whichever account called that contract. So that was the example I wanted to show you, and that also concludes the presentation. So thank you very much.
How far in the process of doing this one verification?
Yeah, so that's a really good question, so I was working on the formal verification of the GNO token, and I thought I had verified it, but it's like this mathematical flaw in my argument that I made. Basically, to reduce it to one sentence, the GNO was constructed with 10 million tokens, and for that reason, there is actually no overflow protection in the GNO token, and that kind of messes with the K implementation of ERC20. So I assumed that there will always be 10 million tokens in my proof, but that might not be the case. I didn't prove it. So basically now I will have to prove that there will always be exactly 10 million tokens ever available, and therefore no overflow can ever happen, which I don't know how I'm going to do. It's a pretty hard thing, but you can always, like, if you don't know something to do with formally, then you can provide a pen and pencil proof, mathematical one that is much easier to construct than execute.
And basically,
but I'll talk about all the formal verification next time. That's why I wanted to divide it into two presentations, so that like you'll see exactly what I'm working on, the symbolic execution, the writing specifications, and we'll build on all of this that we learned today. Any other questions?
Just one comment to the precompiled versus opcodes.
Yes.
So one simple reason why they use precompiled is because obviously there's a very limited amount of opcodes, but you can have almost an arbitrary number of precompiles, because an arbitrary number of addresses that you can use.
Yeah.
Yeah, I think that was the main reason, and because you want to use opcodes only for things where you know they will be frequently used. And the the precompiled they introduced, they were not sure if that's actually super important. So they knew like SHA-3 will be super important. They didn't know this about SHA-256, so they made this one precompile.
Yeah, I think that makes total sense. Yeah.
And it's a little bit more expensive to use a precompile because you have the regular overhead that you have when you take with other contracts. But yeah,
Why don't we generate just the instruction set that was already to do the actual SHA-3?
Oh, so for SHA-3 there is the opcode.
Yeah,
For SHA-256, using a precompile, it's not using like precompiles. They are not using like Ethereum opcodes to operate this. It's just that to access this precompile, you make a call to this contract instead of just placing the opcode into the bytecode. Yeah, so if you use SHA-256 or EC recover in a smart contract, then what's relatively do it will actually call the precompile instead of having like an opcode for EC recover, which doesn't good.
You can also think that with compiled contracts, you don't need a specific implementation in the compliance because it's already in bytecode. Right? Compiled contract.
I don't
No,
I don't think that's the case.
Okay, so it's like not necessarily in EVM bytecode then, it can be implemented in anything.
Yeah, but imagine that you have a new client, the precompiled contract, there is a bytecode for that precompiled contract, right?
Yeah, you can surely just use this, but you could also have native.
Yeah, of course, the client can decide to implement their own version, but
Right.
you have a hard fork and you don't have resources to do it, and you have a client, you don't need to implement it. You just need to secure the compiler.
Yeah.
Also, if you can ensure that your implementation is safe.
No, I think precompiles, they're actually, like, I would have to look into that, but I think they are implemented into native client language.
Yeah, for example, as you mentioned, you can also run KEVM as a node on the Ethereum network, and here is the actual semantics of the precompiled contracts in K. So, for example, SHA-256, all it does, once it's called, it immediately halts, and whatever is passed to it, it will just call SHA-256 on it, where SHA-256 is an internal K function. So K has Java and OCaml and Haskell backends, and I'm guessing SHA-256 will be implemented in one of those backends. But you're also right. I mean, it could also be the case that they will use a pre-created bytecode, such as C++ output. It could be one of, yeah, both options are fine. Cool. So thank you very much. And where's the lunch?